We're going to get underway now, and as other people drift in, they can just join us. Welcome, everyone, to this meeting of the Healthy Planet Action Coalition, where we have the pleasure to speak with Russ George. And so, a few words of introduction. As I've just said it in my terms, our world ocean is anemic. It's short of iron and crying out to us for more iron. And we're saying, I know we have to do an energy transition, so we can't put our iron into the ocean. And it's pretty mad world that we're in, because the world really needs more iron in the ocean. And I think Russ is a great pioneer of that work. So it's great to have him here. And people would know the 2012 Haida Salmon Restoration Project and all of the discussion about that, and that's one of the things that I'm interested to focus on, and the whole question of ocean pasture replenishment, as Russ calls it, against the language of a lot of the climate science community. So welcome, Russ, and over to you.
Okay. Well, thanks, Robert, for inviting me here. It's an important topic. It's all about, the simple fact that the high CO2 in the world's atmosphere, high and rising, has caused the grass to grow all over the planet. And grass grows in regions that we call dry lands. And when the grass dries up in the dry season and the wind blows, the dust blows in the wind. But high and rising CO2 helps grass grow better without losing as much water through what's called evapotranspiration. So the dramatic decline of evapotranspiration, water loss, in dry lands of the world has resulted in a cataclysmic decrease in the amount of dust that's circulating in the world's atmosphere. And dust that blows off the land, is a bad thing if you're downwind and you're in a dust storm. But if you're in the ocean, it's a blessing, right? But China, for instance, has lost 80%. There's been an 80% reduction in the amount of dust blowing out of China, which is China and Mongolia. The Gobi and Taklamakan deserts provide the majority of dust for the whole of the northern hemisphere, right? And that's down by 80% since 1960. So you would imagine that such a vital mineral it might have a huge impact in the 72% of the world that is ocean, right? Where much of that dust, that missing dust was nurturing plant life. And so we have had this, you can do the math, right? There's been a cataclysmic decline in ocean photosynthesis as a result of the diminishment of iron that's carried, which is the most vital constituent of that dust in the wind. And so what I call this ocean, I call it ocean iron replenishment, because we need to replenish that dust, right? That mineral dust. And that's pretty much the most urgent situation on the planet. And it is by far a vastly larger and greater ecological and environmental impact that has been worsening decade by decade than is what we call climate change, right? Because this is really not climate change. This is ocean change, right? And the CO2 and the mechanism by which CO2 is impacting the ocean is not through its thermal process, not through becoming a greenhouse gas that's warming the atmosphere. It's killing off the ocean productivity through the process of diminishing photosynthesis on the planet, right? and which is and the vast majority of photosynthesis on this planet, on this blue planet, takes place in the oceans, in the blue part. So, ocean change as a result of high and rising CO2 is the most measurable and significant environmental and ecological impact that's been occurring on the planet. And it's far in excess of the impacts of climate change. So, the late great John Martin, when he started studying this back in the 1960s and early 1970s, set himself to the task of doing the very precise quantitative science of understanding the potency and the role of iron in ocean ecology, and also the role of ocean plant ecology in the world, in the management of the climate of this planet, because and so he's the guy who started this. So this has been going on for, this work has been intensively researched for 50 plus years, right? And
And yet,
some things
Russ,
that what?
you've faced major barriers to the deployment of iron in the world ocean, and I what I'll just check with you. How long would you like to speak for initially, and at what point are you interested to open up to a conversation?
Oh well, I'm happy to just have it be a conversation, from the beginning here. It's I'm sort of assuming that most people here have have read about this story or heard the story a bit. I've got a bit of it. This has been a bit of an introduction as to
Well,
my out of the box point of view that the crisis on this planet is ocean change, not climate change. But climate change is a problem, but it's a secondary problem, not a primary problem.
but you partly said that the higher CO2 that's suppressing the dust,
Right.
uh, and so that's like a feedback from higher CO2 is
Right.
more greenery on the land, less dust going into the ocean, less iron into the ocean. But for those who might not be familiar with your history, Russ, I might just mention uh, that you worked with the Haida community in British Columbia to deploy iron in a way that was targeted to increase the salmon run in the North Pacific by targeting fingerlings, and it from your point of view, it appeared to be quite successful, but the success of that work was disputed, and not only that, but the whole uh, project was vilified and was effectively banned under the London Convention and Protocol, and was smeared as the dumping of waste. So it's quite a
Well,
bad.
it was in the world of social media, the word banned under the London Convention, London Protocol has come up, even though that's an absolute falsehood, right? The London Convention, the London Protocol on the disposal of red listed toxic materials in the ocean, right, is a very, very specific subset of the international law of the sea. And many nations are not signatories to the international law of the sea, such as the United States of America, right? So they've never ratified and accepted that. So they all say, so automatically they don't accept the subsets under that. But the London Convention, London Protocol is very, very legally specific. It specifically mandates for the prohibition, the regulation, actually, of the disposal of listed substances, right, at sea. So, so putting iron in the ocean, iron has never been on the red list of the London Convention, London Protocol, right? So therefore, people who have fomented discord in this topic by bringing that subject up and suggesting it's a ban have been committing outright fraud, right? It's not nothing less. It's just an absolute legally, lawfully provable fraud to state that the London Convention, London Protocol has banned this, right?
Sorry, that's the impression that has come up. What we'll do, Russ, is I'll invite people to raise their electronic hands, or if they can't work that out, to wave to me somehow, and
Yeah,
so we'll just go to people as they raise their hands, and I'll hand it over to Seb Clark.
sure.
Hi, Russ.
Hi.
Russ, we saw from satellite photos how the area of ocean which you fertilised became turquoise and brighter. Have you estimated the amount of extra albedo that would have been caused had you made it wider, and how much extra global cooling that would have resulted in?
Well, I have some very comprehensive models that I've used to study the albedo effects, and I can tell you, I mean, number one, we never fertilized it, right? We replenished iron to the ocean, right? For fertilizers, when you apply fertilizers to lands or ocean waters, right, or through accidental purposes, right, you're typically changing the concentration of nitrates or phosphates by parts per million, right? Whereas when you replenish iron in the ocean, you're changing concentrations by parts per trillion, right? Or maybe parts per billion. So it's a dramatically lesser effect, right? So that's the term fertilization was crafted by people in the ocean science community back in John Martin's day, following the original experiments after John Martin died, right? Where people who were your basic anti-technology Malthusian personalities that we know full well, exist in a lot of people in the world, who think that anything that humans do must be negative to this natural planet of ours, right? And so they chose the term iron fertilization because in every instance of where fertilizer is associated in the ocean, in the literature, it's a bad news story, right? So we talk about fertilizers running off agricultural lands and running down rivers and entering the sea and causing massive over fertilization of constrained coastal waters and vast algal blooms and the production of dead zones, right? And that's a truism, right? That's what fertilizer in the ocean does. But nobody has ever intentionally fertilized, any significant areas of the ocean because it's simply not economically feasible to apply fertilizer in the ocean and raise the concentrations of nitrates and phosphates by many parts per million, right? It's just the cost and the pure logistics of doing that makes it an impossible undertaking. So when the cabal that wanted to poison this topic, created the term ocean iron fertilization, and those that continue to use it today, right? That was their intent, was to command the language and spin master and control the story, right? And force it into a negative context from the get-go. Right. So so the reality is John Martin and other people who had studied this for decades, and the study of iron in the ocean and its potency with phytoplankton goes back to the 1930s. So it's not a new subject, right? This is a topic that's been researched for 100 years, right? So it's not a frontier or pioneer topic, right? It's an old piece of science that's been going. And the best numbers are that for every atom of iron that gets into the ocean, that atom of iron stimulates the photosynthesis that results in the capture of 1 million atoms of carbon, right, by photosynthesis. So a ton of iron, results in the capture of 3.67 million tons of CO2, right? So that's the kind of potency that John Martin was onto, right, when he was tackling the subject. And that's what led him to his, when you go back to John Martin's math and you say, how did you get to that famous quote, John, where you stood up in front of the Ocean Science Committee and said, give me a half a shipload of iron, I'll give you another ice age. Because iron can stimulate enough photosynthesis to draw enough CO2 out of the atmosphere to pull the carbon dioxide greenhouse blanket, right, off the planet and plunge us into an ice age. And he had shown that had happened on numerous occasions. And the math that he used is pretty simple to come to, right? So that's what drove this. And that's what scares the bejesus out of people in the green community, for instance, who would like to brand this as some kind of Malthusian geoengineering horror, right? That humanity ought not to touch, right? Because a half a shipload is not very much, right? John Martin's ships, he was talking about a ship that might be 100,000 tons, right? So if 50,000 tons of iron is sufficient to cause the planet to go into an ice age, especially given that China buys 6,000 of those shiploads of iron every year from Australia to make steel, right? So if 1/2 of one of those 6,000 shiploads of iron were to happen to go into the ocean and send us into an ice age, you have the makings of a good horror movie, right?
Okay. I might just check with Sev if that answered your question. Sev, want to come back?
I'd hoped that Russ might have been able to give us an estimate for what he thought was the albedo increase, which his experiment showed.
Well, I'll tell you this: the cooling potency of the albedo increase of that project compared to the tons of carbon dioxide captured and sequestered, the albedo effect was larger than the carbon capture effect. Yep. in the process by a substantial margin, right? So so the whole argument in this that people have attacked this, they've said, well, how much carbon sinks? How much of the captured CO2 sinks and is therefore sequestered? And let's argue what that term of sequestration is, right? And they want to engage in this debate about it. You can ignore that entirely and say, well, what's the value of the albedo? The albedo is vastly greater than the carbon capture value, right? So in terms of CO2 equivalents, right? If you take CO2 equivalents and convert it, if you take albedo and you say, how many watts per square meter did we cool? Right? And what is that equivalent in tons of CO2 equivalents? The albedo is the big number, right?
Russ, let's go on to Greg Slater.
Sure. Thank you. Well, thanks for being here. I've of course heard about your story for, God, so, I mean, since it happened, and it struck me as unfair just on the face of it, even though I didn't look into it beyond the popular press. But it's great to have you here to give your view in person. In the things you've said so far, there have been very many interesting things to me. But I'm wondering in particular about your framing that the problem of the loss of productivity of the ocean and dwarfs the problems of climate change. I mean, I've very much been interested in concern about climate change for decades, and I mean that is a strong statement, and I wonder why it is necessary to minimize the climate change problem relative to the collapse of the ocean.
Well, I'm not meaning to minimize or discount the climate problem. That's a true problem, in and of itself. It is a
Mhm.
very substantial problem.
Okay, so I
But
mean,
in
the
the
fact that
context of, yeah,
yeah, I mean, on the face of it, on your description, it is extremely valuable to be tested at scale because it provides both these things. And some of the other techniques that people here have provides both replenishment of the oceans and either carbon CO2 capture or reflectivity, and therefore that's all to the good. I mean, my interest is in particular of either of the possibilities for CO2 sequestration, or which I wasn't aware of, or but I guess I didn't appreciate the possibilities for albedo increase that you just discussed. And I guess what I'd be interested in is the closest to a technical paper or papers that you have generated on the basis of your models, so I could just learn the details. And I mean, again, I assume you've had enormous difficulty publishing in the scientific press, but nonetheless, I assume you've made your own reports for distribution of things which give the technical details of your estimates and of the models. Those things would be very interesting to me if you could provide those.
yeah. I mean, I mean, to say that we run into a buzzsaw of in the conventional scientific press is an understatement, because we've been up against this determined effort by academics and institutions who act as a guild or a cabal to defend their exclusive privilege in science in many areas, right? And I mean, the most egregious case of recent times is a couple of years ago, 2 or 3 years ago, the U.S. National Academy of Sciences published a massive report on called Ocean Carbon. And they described all kinds of processes in the ocean by which carbon is managed in ocean systems. And they described the Haida project. And in parts it looked like a very positive report, and I still extract pieces of it and use it as a positive reference material. But at the they also made a group of recommendations, a select number of recommendations for the report, and the recommendations included, they said, they cited the London Convention, London Protocol inaccurately and completely unethically. They didn't cite the legal foundations of the London Convention, London Protocol. They said it was a problem. They cited it, and they said because of these problems, these issues, this controversy, this subject should be limited. The research in this field should be limited. And number one, no research projects should be encouraged. Iron projects in the ocean should be encouraged, but they should take place only within the 12-mile limit waters of nations, right? And so, and they should only apply very small amounts of iron, in the order of 1 to a few tons, right? Where's their recommendation? Well, in waters within 12 miles of shore, any place on this planet, those waters are iron replete. They're stuffed with iron. So under no circumstance could you ever engage in the fantasy of conducting an iron addition experiment in iron-rich waters, right? And expect to observe an effect. So that was a unethical, fraudulent recommendation by the U.S. National Academy of Science.
So, Russ, that's an example of the science community bias and prejudice against the need for more iron in the ocean. Do you mind if we just go on to a couple more people got comments first,
Oh
Oswald?
yeah, absolutely.
We'll just move through people.
No, take you.
We've got a really good audience. We've got 27 people here today, and we have to give as many people as want to a chance to say hello and speak.
Sure.
So, Oswald,
Okay.
please.
Yep. Go for it.
Oswald Peterson is muted.
Do you hear me now?
Yeah.
Yes. I'm Oswald Peterson, CEO of AMR. It's an atmospheric methane removal company in Switzerland, and we plan to disperse iron 3 chloride or ferric chloride, or ISA, sometimes called iron salt aerosols, over the ocean, over the open ocean or international waters in the subtropic areas. The plan is to distribute around 300,000 tons annually. And I would like to hear what you think about this plan. Is it something that you would support or not? Or did you ever hear about this? Or
I have heard about it. Yeah, I have heard about it, and I've talked at length with some of the proponents of it, over the time. I struggle with it, right? I don't have a problem with the chemistry, right? I think the chemistry probably is, functional. I'm not sure. I haven't spent enough time to do the business economic models on it myself, But my gut reaction is it would be difficult to make it. My own personal opinion, it's difficult to make it make financial sense. And it also ignores the fact that there are vast regions of those oceans which are methane sources already, right? So, and the reason why they're methane sources is because the ocean, those areas are iron deplete waters. And so as a result of those waters being iron deplete, their ecology and biology has shifted to the point where they're aerobic methanogenic regions of the ocean, right? Because of the depletion of mineral dust and iron. So a more practical way to limit the methane would be to put the iron in the water, right? And we replenish the iron that's gone missing, and bring that ecology back to its normal state of health, where it's not methanogenic, right? And producing methane, right?
So, Russ, the iron salt aerosol method, by adding ferric chloride to the atmosphere, that iron eventually finds its way into the ocean in a very diffuse form. So Oswald, did you want to respond to Russ?
Sorry, I had to go open the door. I didn't hear the question, I'm afraid, so I cannot respond, I'm afraid.
Okay, let's just move on to Brian.
Thank you, Russ. It's good to see you.
Yeah, good to see you again, Brian.
Yeah, two questions. For many species, the subtropical Pacific Ocean, for example, is nitrate limited, not iron limited. And I realized that nutrient limitation is species specific. So my first question is going to be, for which species do you claim that subtropical and tropical ocean is iron limited as opposed to nitrate limited? Pacific is a good example because there's excess phosphate. The second question I'll ask you relates to the ramifications of the law of the sea treaty coming into force in January. Thank you.
Well, we could get into a long academic discussion about the reason why the oceans might be nitrate limited, right? I think that's because the nitrogen fixers are limited, right? And so I believe those waters are there. We may not say they're as iron, because they're nitrate limited. Then that tends to paint the picture that allows iron to be more available, right? Because there's less nitrate to facilitate the consumption of that iron. But I believe they are. I believe the whole of the world. The evidence on the diminishment of dust circulating in the Earth's planet is so profound, and it's a direct line. If you have an 80% reduction of dust, which is the primary source of iron to the world's oceans, right? The aeolian dust. You have to have a dramatic reduction of iron, right? You have to have a
So I'll grant you that, let's say in China, we've got a lot of decrease in dust. Now, an exception would be the subtropical Atlantic, where you've got copious amounts of dust that are coming off the Sahara and going across the Atlantic. How would you contrast that pelagic ecosystem compared to, say, the Pacific?
Oh, it's a dramatically different system, right? So the ocean has as many different ecosystems as relatively speaking as Earth, right? So it's hard to say, you can't call the ocean one ecosystem, right? It's like saying the Sahara Desert and a redwood forest are exactly the same because they are terrestrial ecosystems, right? They're obviously enormously different. So the ocean is vastly larger than the terrestrial space on this planet, and I think has a vastly greater number and greater diversity of unique ecosystems, right, in the ocean.
Right. Yeah. So what's interesting is, let's consider that the subtropical Atlantic might be an iron replete environment, and the Pacific might be iron limited in some way. How would you contrast those two as an example?
Well, they're just very, very different, right? I mean, it's I wouldn't say I've ignored the dust in South Atlantic, right? I mean, I cite it because when people say, "Oh, you're going to put 100 tons of mineral dust into the ocean," how horrible that is. Whereas we know that 600 million tons of African dust actually goes across the Atlantic and lands in the Amazon basin. So 100 tons versus 600 million tons. And we don't see any deleterious effects in the intensively dusted South Atlantic, like, northern South Atlantic.
Do you see the productivity increase? In other words, we've got all this dust hitting the Atlantic. Are you seeing the productivity increase in the tropical Atlantic?
It's a bit higher, but the ocean is this is the reason why I coined the term ocean pastures many years ago to describe this, is to try to have a metaphor that people were familiar with. So if you have a pasture on land, we know that we can't intensively manage and harvest from that pasture year after year after year after year. We have to let the pasture lie fallow to recover, right? Especially natural pastures. We can harvest from them so long as we honor their requirement for fallow periods. Well, so when you have an intense amount of dust landing in a patch of ocean, you have that ocean has no fallow cycle, right? And so that ocean crops out, right? The South Atlantic is over dusted, right? Mm-hmm. So it's not dependent. It's not an iron dependent ecosystem, right? Mm-hmm. It's purely nitrate and phosphate dependent, and it's going to and it's very large. And so when you have these large areas of ocean that get dusted, and the process of an ocean pasture going through a fallow cycle means that it has to recover. Well, the way ocean pastures recover is by mixing from the surrounding waters. Well, if the area of dusted ocean is very, very large, like the Saharan dusted, the African dusted South Atlantic, the mixing time for that patch of ocean that receives that dust is so long as to eliminate its ability to lie fallow and to recharge itself from surrounding waters. Whereas in other regions of the world, farther away from intense dust sources, The dust lands intermittently, rarely and intermittently. And the natural process is that there's always a fallow period, right? The nature has provided a guaranteed fallow cycle, right?
That makes sense. Yeah. And
Yeah.
that mixing problem is getting worse with unprecedented ocean warming. Since you've got the warm layer on the surface is getting warmer, there's an even greater energy barrier to that vertical 100-meter mixing that would provide
Right.
nitrate and phosphate.
Brian,
Serious problem.
let's move on to your second question about the law of the sea.
Yeah, the law of the sea. I mean, I don't know exactly, what's going to happen. I don't really have a comment on it. Except that the people who are fomenting these discussions in the law of the sea and London Convention, London Protocol, and the Convention on Biological Diversity and things, these are personalities who are focused on their political goal of punishing and eliminating fossil fuels and the oligarchy that the fossil fuel industry represents, right? And they are willing to bet the life of the planet for their political goal of destroying the oil oligarchy of the planet. And so when they interfere with the collapse of the ocean, right, and the remedy for the collapse of the recognition of the collapse of the ocean and the remedy for that, which John Martin brought to bear 50 years ago, 40 years ago, they're committing an incredibly egregious sin against nature, right? And what can you say, right? So I don't think that those policies, they're going to. I don't think the world is going to take the bait and adopt those kinds of Malthusian, selfish goals, right?
Brian,
Thank you, Russ.
Peter.
Yeah, Russ, good to see you again. I think everyone here knows me. Actually, I see a couple of people whose names I don't recognize. So
good to see you,
Peter
Peter.
Fikowski.
Yep.
Yeah, thanks. Peter Fikowski, part of all sorts of organizations on restoring the climate and my book. So, Russ, just a couple technical questions. In the last few years, I've been working to expand the possible productivity of OIF. And I sent you a couple of my articles this morning when I saw you were going to be here. I wanted to get your thoughts about the two processes that I think are critical and have not been discussed in the literature yet. They're adding enough iron to get nitrogen-fixing bacteria to produce the nitrogen needed. And the second one is doing it in a downwelling eddy because the evidence we have from the Orbiting Carbon Observatory is that if there's not a downwelling eddy, then the fish and the zooplankton metabolize almost all of the biocarbon, releasing, giving you a net zero impact on no matter how much phytoplankton are growing. So I'd like to hear your thoughts about those two additional processes. Enough iron to grow.
Downwelling eddies is easy, right? Because the eddies are not are toruses, right, in the ocean. So the difference between a downwelling eddy and an upwelling eddy refers to whether at the center of the eddy, whether the water's coming up the center of the eddy or going down in the center. But at the edge of the eddy, the water does the opposite. So in an upwelling eddy, that the water comes up out of the center of the eddy, it flows out to the edge of the eddy, and it downwells at the outer circumference. So all eddies have both an upwelling and a downwelling component, right? And they are in fact in balance. So this idea that upwelling eddies, will not allow the fixed carbon, the biological carbon, to sink, right? But will sustain that in the eddy where it's consumed. That's just patently absurd, as far as I'm concerned, because in observation we see the downwelling. It would be nice if you have a nice vigorous whirlpool. This kind of goes in the concept of our vision, everybody's vision of a whirlpool, right? And we say, okay, well, if we're growing stuff at the top of the ocean and we have a lovely whirlpool that sucks all that surface growth and punches it down into the depths, wouldn't that be a great way to transport that carbon into deep sequestration, right? And yeah, it works. That's good. I would, if I had a choice between choosing an upwelling and a downwelling eddy to put my dust in, I'd choose a downwelling eddy, right?
Right.
But
Okay,
but
good.
I know it. But I know that same carbon will downwell at the edge, right, of the eddy, right? Because it's really a torus. It's not an eddy. It's not a whirlpool. It's a torus, right?
Okay, good. So hopefully we'll get our paper out soon, and you'll see the evidence from the orbiting carbon observatory. How about adding enough iron to get nitrogen fixation working, like on land farming?
Well, cyanobacteria, which are the principal nitrogen fixers, are very much dependent on iron, and they're very competent at grabbing iron and increasing their productivity, right? So whenever iron goes into an iron deplete ocean, the very first and the cyanobacteria, the bacteria are faster to reproduce and respond than the chlorophytes, right? So I think by ecological definition, the cyanobacteria the first thing that happens when dust lands in the ocean is it stimulates a massive production of cyanobacteria and an enormous amount of nitrogen fixation. And that's the system has evolved. I think the ocean, nature knows that if it has all the nutrients, if suddenly it has an abundance of nutrients available and it's short on nitrate, it sure as heck better make nitrate, or it's not going to avail itself of this, blessing of dust. So the ecosystem has evolved to make use of that. And you always produce nitrates. And phosphates are heavily recycled. I think there's, on the other side of the coin, the natural recycling system in the ocean, that's powered by the biological pump, by the copepod pump, right, is a fantastic phosphate recycler, right, as well. So,
Russ, if I could just mention, Peter has quite an interest in the role of volcanoes in adding iron to the world ocean, and that must be a topic you've studied quite a bit. Like you've discussed that in terms of the impact on salmon yields.
Yeah, no, I've been studying that for a long time. I remember in my very first meeting with John Martin back in 1989, he brought up the subject of volcanoes as one of the sources of iron for the ocean. Yes, unfortunately, volcanoes don't happen in a ecological scheme. Like they're not driven by ecological sources. So, if a volcano erupts in the wintertime, in a cold, dark ocean, and dusts that ocean, the minerals it deposits from the ashfall won't be of much use because photosynthesis is suppressed. Whereas if the same volcano were to erupt at the beginning of summer, you would have a fabulous effect, right? So volcanoes are they're natural laboratories, and volcanoes can prove beyond a shadow of a doubt. There's never been a single scientific report of a deleterious effect resulting from a plankton bloom that was stimulated by a volcano, even though we have plenty of examples of that, and plenty of people have been involved in studying those. No one observed a deleterious effect. No one saw an oxygen depleted dead zone being created by a natural dust event, right? There's no example of that in the world's oceans, right? In the world science literature. So volcanoes are a great natural scientist, right?
Peter, did you have any further follow-up?
Yeah, well, yes. So Russ, when you get a chance, take a look at the paper I sent you where we're looking at major eruptions over the last 500 years, of which there's 9 which produce significant cooling of the atmosphere. And of those 9, 3 of them produce significant CO2 removals. And so the only 3 out of the many volcanoes that made notable removals of CO2 visible from ice cores or from the Keeling curve are the ones that were right next to either upwelling or downwelling eddies. And
Yeah,
so
of course, eddies are small, right? Eddies are 100 to 150 kilometers in diameter, right? Whereas, volcanic ash falls are thousands of kilometers in diameter, right? So there's always an abundance of eddies, right? In any given patch of ocean, right?
No. Most of the ocean has very few eddies. Just
Well, there's
maybe.
about, I recently, thank God for AI. I recently had AI count the eddies on the planet Earth, and so there's under 10,000 of these mesoscale eddies on the ocean, on the Earth at present. But 10,000 is 10,000, 50,000 square kilometer eddies is a pretty significant number, right?
Yeah.
Russ, let's move on to Paul Beckwith.
Yeah, hi everybody. Hi Russ, thanks.
Hi.
The first part of my question was natural sources of iron. So you've mentioned volcanoes, volcanic ash. What about things like wildfire ash? I know that's really good fertilizer. Whenever there's wildfires in Canada, the lakes tend to proliferate with plankton. Also, we think of Saharan dust being blown as a big dust source. So, are there some other sources, and can we enhance the natural sources by, instead of adding iron to the ocean, just add it to, say, the Sahara Desert dust, or put it in a caldera of a volcano that's erupting, or I don't know. So what form is iron reaching? What form of iron is in the ash of volcanoes, the ash of wildfires? Like what size are the iron particles? When we deploy dust clouds of iron, if we do it from ships or blimps, dirigibles over the ocean, etc., what latitudes would we want to deploy them at? And I'm sure the size is crucial. Like the smaller the iron particles, the longer they'll be buoyant. It'll take them a lot longer to disperse in the water column. They'll be more widespread. We can get way more coverage than if we put them in the ocean off a boat. So what is your thinking on the best way to actually deploy, iron in the ocean at this stage?
A few years ago, when Australia was on fire with its horrific brush fires, and the whole world was, seeing horrible photos of koala bears that had been burned in the fires, and the smoke plumes from the Australian fires blew to the east into the South Pacific. A couple of years ago, papers started coming out, looking at the plankton blooms that were a direct result of the smoke, of the iron in the smoke from the Australian fires, because there is a little bit of iron carried in that smoke, right? And it's naturally a very small size. Whereas volcanic ash, when volcanoes erupt, it's a pyroclast, it's a pyrophytic material, right? It's hot. It's typically some form of volcanic glass is what volcanic ash is. So if you want to embed nuclear waste for all eternity, you do what's called glassify it, right? You mix it with glass, with molten glass, and the uranium, the metals, right? The radioactive metals in the waste become inaccessible because glass is so insoluble, right? So enduring to the planet. So volcanoes have very low volcanic ash has a very low concentration of iron, but even more so, that iron is extremely unavailable, right, to the ocean, right? It's extremely insoluble. So volcanoes are the worst way put
Right.
iron in the ocean. But volcanoes tend to be very big things, right? You know, so
Yeah.
when you have, you know, these giant volcanoes, like the Tonga volcano that erupted a couple of years ago, created a vast plankton bloom in the South Pacific where the ash landed, right? It was a massive uh, ocean color event that took place there.
Just on Paul's question of other sources of iron, a big one used to be whales, but that's been depleted.
Well, whales. I mean, you know, whales. You know, the ocean, the iron in most of the world's oceans, where iron is in a depleted state, which is most of the oceans far from land, right? I mean, iron comes from land. So any place where you're in proximity to land or in shallow water, there's, you know, like I always tell people, if you look at the dirt on land, any place on the earth, and it's tan in color, it's never less than 1% iron oxide, right? So tan colored sand is 1% iron oxide. Whereas if you look at red dirt on this planet, it's typically 3% hematite iron oxide, right? So that's a, you know, 1 part per 100 or 3 parts per 100, right? Well, the ocean can survive at levels of iron, at low levels of iron, down to a part per trillion. 1 part per trillion of iron in ocean water, which is 3 parts per trillion, is the number John Martin pegged in his research years ago. He said the vast majority of the open ocean away from obvious iron sources is sitting at 3 parts per trillion iron, right? Well, you go from 3 parts per 100 to 3 parts per trillion. There's a lot of orders of magnitude there, right? So the primary source of iron near shore is the shore, right? Is the earth, like the land. But iron being a heavy element tends to sink, right? It's also very insoluble. It's also the most desirable element in the ocean, right? In trace amounts. So it's scrubbed, you know. So the ocean's ecology is a fabulous biofilter for iron, right? So coastal waters are scrubbing every atom of iron they can get out of the water, and the rest is sinking. So almost nothing gets offshore, you know. And there are exceptions to that rule, but generally speaking. So the problem with iron, you know, and natural sources, so really the bulk of the world's oceans are dependent on dust in the wind. And high CO2 makes the grass grow on land because plants breathe just like you and I do. We breathe in air, we do gas exchange across a wet membrane in our lungs, and grass do it in their stomata, right? So they breathe in they take a breath of air, they breathe it into the inside of the plant, they expose it to a wet membrane to do gas exchange. And plants want the CO2 out of the atmosphere and they want to put the oxygen back in. And so when they're doing CO2 exchange across that wet membrane, they have to evaporate water into the atmosphere. That's called evapotranspiration, right? And high CO2 makes evapotranspiration far less of a problem for plants. So the dry land grasses of the world are saving moisture because of the 50% higher concentration of CO2 in the atmosphere than there was before the industrial age, right? So if you were in a hospital and you went on life, and the hospital said, let's give you oxygen to keep you healthy, right? They technically put you on 10% additional oxygen, right? Maybe 20% if you're in really dire trouble, right? Maybe if you're near death, they put you on an even higher concentration. Well, when you're healthy, if you had 50% more oxygen, you would breathe a fraction of the amount of time because you'd get all the oxygen, you do all the gas exchange you needed with far less respiration. So you would evaporate. So if we were in a cold room, and we all know when we're in a cold room, when we exhale, we can see the moisture in our breath as a cloud of fog, right, out of our breath. That's the moisture. that we're exhaling. And every blade of grass, every plant exhales that same cloud of moisture with every breath it takes. Except now plants live in a 50% higher CO2 environment than they did 100 years ago. So they're breathing less, so they're exhaling less water. So the amount of water that's being saved by plants, it doesn't have any effect on a plant in a moist area, right, in a rainforest.
Right.
But plants that live in dry places where their biology is limited by their drying out at the end of the wet season, as they go into the dry season, every molecule of moisture that plant conserves and saves means that plant can continue to be green for a little longer. So high CO2 means more grass growing. And where grass grows and it's green and it covers the ground in the wet season, we call that good ground cover. It prevents the dust from blowing. So more grass growing, less dust blowing. All right? It's a really simple ecological truism.
Russ, I'll just give Paul a chance to come back before we move on.
Yeah, I just wanted to say quickly, I'm just on the Wikipedia page on John Holland Martin, and it's a fascinating read on his life and his work. He died of cancer when he was 58. It says here, prostate cancer, 58. So, but anyway, it talks about his work. Also, it always strikes me as one of the remarkable things about life that chlorophyll and hemoglobin are almost exactly the same molecule. In hemoglobin, the center is an iron molecule or atom, and in chlorophyll, it's magnesium, I believe. But it's almost, you look at the structure of both those molecules. I mean, they're both vital.
It's magic in chemistry because it sits in the middle of the periodic table, which means that it has a very frivolous electron vacancy, right, sitting in its outer shell, so it can very easily engage in chemistry, right? So,
Paul, it's nice to see Newton there with you, your dog.
Well, he's my wife brought me some food while I was on the call, so he's after it. I'll just bring the camera over here. So
yeah, there he is.
Newton,
this is the star of the show. So he's been chewing on my hand while I've been trying to talk, thinking, no, not right now.
I thought it was a blanket in the background.
And the site you share, Paul, on your videos is completely amazing. I listen to you whenever I can because just getting up to date on the latest scientific papers all across the climate space, it's great. I'm going to move on to Dennis Garrity.
Oh, okay. Thank you, Robert. Russ, it's great that you could join us on this discussion today. Now, I know from our recent conversations, you and I, that you have some major plans for developing a new project initiative on ocean pasture management. I wonder if you could give us a brief picture of your current plans.
Well, I've been at this, since John Martin gave a talk in 1989, 1990, and a friend at MIT was in the hall when John Martin gave the talk and knew that I was interested in. I was doing nuclear physics at the time, but I'd been an ocean ecologist and plant ecologist, my friend sent me this cartoon that was in the Boston Globe, and he faxed it to me, right? So the next day I got a fax out of a cartoon in the Boston Globe, John Martin in the cartoon saying, "Give me a half." The world, the greatest problem in the world is global warming, but global warming is controlled by the plankton in the ocean, and the plankton are controlled by the dust in the wind and the iron. So give me a half a shipload of iron, I'll give you another ice age. And so courtesy of the modern world of fax at the time, not quite pre-email, but darn close, right? I think at the time I was paying per character for my email, right, with my email service, right? It was like sending a telegram, and so I got this fax of John Martin's cartoon, and I hopped I was living in Palo Alto, and I hopped in my car and I drove down to Moss Landing Marine Laboratory and knocked on John Martin's door, and he was the director of the Moss Landing Marine Lab. And he was so very gracious. I thought I'd get to talk to him for a minute or two, and I ended up spending the whole day with him, right? And he gave me this, fabulous personal tutorial on this topic. And I was infected by it, but I was, it wasn't something I could dive into in time.
So, Russ, Dennis asked you about your current plans.
Yeah.
Well, so ever since, about 10 years later, I was hired by the Canadian energy industry to develop a forest restoration program in Canada to plant enough trees to capture enough CO2 from the atmosphere to offset the carbon footprint of the Western Canadian fossil fuel industry. And that's because I'd started the second largest tree planting company in Canada in 1972. And so in 1999, the energy industry said, well, you're the best tree planting brain in Canada. Plan a tree planting program to capture CO2 in forests. Well, after spending more than $1 million of industry's money doing a careful research project, I couldn't find enough empty land in Canada to plant enough trees to make a dent in their carbon footprint, right? And I had to report to 7 vice presidents in the big energy companies, and I said, sorry, we can't do it by planting trees. But the good news is John Martin says we can restore the seas and do it in a heartbeat, right? Manage the CO2. So I started that, and ever since I've been designing projects, right, and trying to get out to sea, and I'm still at it. I'm I'm getting older and grayer, okay, but I have a number of I keep getting contacted by nations all over the world and asked to make presentations to governments and institutions all over the world, and to replenish the ocean, restore the ocean, bring back the fish, bring back the seabirds, provide a mechanism to capture and sequester CO2 as biological carbon for the long term, and solve ocean acidification, because only biology can compete with the acid forming reaction of the 2 trillion tons of CO2 already in the atmosphere in the fossil fuel age, right? We can't add 2 trillion tons of antacid tablets to the ocean. It's not possible to create a mining industry. We need a mining industry 10 times bigger than the global mining industry to provide minerals to neutralize ocean acidification. But because of John Martin's 1 to 1 million potency of iron in managing CO2, right? We can do it with iron in partnership with phytoplankton, right? And then albedo, and every plankton. When John Martin died, a couple of months before the first iron expedition experiment went to off the Galapagos Islands off the coast of South America, his dear friend Dick Barber from Duke University took over the mission. And when I met with Dick years later, I asked him, I said, well, how was that project? And he says, well, it was a fabulous project. We put our couple of tons of iron into our patch of ocean 300 miles west of the Galapagos. We knew it was going to work. We'd sailed beyond the patch into the night, and we'd come to collect background data outside of the treated ocean. And when we got back to the patch in the morning, he says, I woke up in my bed, in my bunk on the boat, just before dawn, smelling a strange smell in the air. And he says, it pulled me out of my bunk. He says, so I got out of my bunk in my t-shirt and underwear, made my way to the back deck of the boat. And when I opened the door onto the research deck at the back of the boat, half the crew was standing there with their noses in the air, sniffing. And we could all smell this incredible strong smell, and we had no idea what it was. And he says, but dawn was just about to break. And he says, as the sun came up, we could see the ocean had turned from blue to this beautiful emerald green. And he says, and I knew instantaneously what the smell was. It was the smell of fresh mown hay, right? So the grass had been growing in the ocean. Plants, the smell that he could smell, right? The phytochemicals from the phytoplankton are the very biological molecules that are the principal source of cloud nucleation sites for moisture in marine air. So plankton blooms flood the air with the fragrance of the bloom. That produces clouds, and clouds are albedo.
Dimethyl sulfide.
It is one, but that's the common one. But there's 100 chemicals, right, or 1,000 chemicals of it.
I know
right?
Brian's an expert on this. Russ, I'm going to go back to Dennis and just ask if he can give us a comment on the Preventing 2 Degrees conference that he's managing in 2 weeks' time. I've put the link to the conference in the chat, and but if you could link it to the iron question, Dennis, that would be good.
Okay, well, thank you for suggesting that. Yeah, we are hosting, that is, the Healthy Planet Action Coalition is hosting a large online conference on October 15th and 16th to really focus on the nature of the global heating emergency that we are continuing to discover is occurring because of this acceleration in global temperatures that has dramatically increased over the past decade. And so we'll be in the conference getting a large number of very renowned speakers on 4 themes. The first is to actually lay out what is happening. Why is the temperature accelerating to such a massively increased extent? Second, we'll be looking at the impacts of allowing this to exceed 2 degrees C by the late 2030s, as the projections are now falling into place. And the implications, of course, of reaching 2 degrees C in such a short period of time are very, very serious. The third theme is to look at the solutions that can actually stop global temperature from reaching above 2 degrees by 2040. As our key goal. It has been the Paris goal, and we're going to be busting through it in no time flat. So we're looking at the solutions that can do that. This is where ocean pasture management comes into play, along with stratospheric aerosol injection, marine cloud brightening, and others. So we're going to looking at how we can put together a package of these practices in a crisis mode to be able to actually stop global temperature from reaching 2 degrees in 2040. And the final session will be discussing the governance aspects of that and how we put together a coalition of climate vulnerable countries that can champion a new climate plan, which is the mission of HPAC, and pull together a commission of scientists, engineers, et cetera, to develop that plan for deployment by the end of this decade if we're going to have any chance at all of keeping the temperature within 2 degrees. My last comment is that this conference is actually aimed at the negotiators of the Belém COP. We have publicized it to all of the negotiating teams, all the delegations, 195 countries, and this is our core audience, of course. But we'll have scientists, we'll have policymakers, we'll have the general public. We're doing a massive publicity blitz. I will send out another reminder to all the HPAC members to participate in the conference, register, and we will also have the recording available afterward for those in unfortunate time zones like Australia. But we are very excited about this. You'll notice from the program the quality and caliber of the speakers we've attracted to this topic. And this, we believe, will be the start of a process of mobilizing the kind of global governance system that can rapidly develop this program of a new climate plan that comprehensively brings together all of the possible ways in which we can combine the means to stop global temperature exceeding 2 degrees. And we will be going on to regional, national conferences next year and further global conferences as we keep the pressure on the UNFCCC to get out of their lethargy, to get out of their delusional processes of negotiation. While Rome is burning, we've got to mobilize the international community on this. And so we look forward to all of your participation. Let me know if you're interested in getting involved in some way in the conference. We're still finalizing all the arrangements, but it's going to be an exciting event for HPAC.
So
Thank
preventing 2 degrees, and the link is in the chat. I've sent that. And I just check in with Russ if you had any comment at this point.
No, I think we have to throw everything we have in our toolbox at this problem, right? So, as much as I'm a believer and champion of John Martin's dust in the wind, so the Geritol solution, he used to call it, all right, for the ocean, it's not enough, right? I mean, my colleague and dear friend Sir David King and I stood up before the Society of Engineers in London some years ago at a talk and had the London media, and Sir David said, yeah, he says ocean restoration with replenishing dust has the opportunity. It might tackle 20 to 30 billion tons of CO2 in the atmosphere every year. But unfortunately, we have 38 billion tons of anthropogenic CO2 going in the air. So it's not a silver bullet. It's not sufficient in and of itself. So we need to throw everything at the problem, right? But this one is cheap, right? If you want a low cost way to put aerosols into the atmosphere of this planet to restore the clouds that have gone missing and thus restore the albedo. Albedo has gangbusters potency on cooling the planet, right? We all know we get cool if we step into the shade on a hot sunny day. It's a lot cooler, right? So, all we need to do is hire the ocean patchers to put up beach umbrellas, right? And cool the planet. And they're
Thanks,
happy
Russ.
to do.
We'll move on to Bob Fry.
Okay.
Yes. Can you hear me?
Yeah.
Yeah, Bob. Oh, you're muted now.
Yes. No.
Unmute, Bob. Okay.
Okay. I'm sorry. I'm just kind of new to this process. I wanted to respond to to Dennis Garrity's announcement of the a conference upcoming, and I really like that summary that he offered. It's become increasingly clear that the schedule is too short to rely on CO2 removal or emissions reduction alone. I think that we have to have things that work on the scale of some major impacts by 2040s and 2050s, and I just don't see enough CO2 removal developing in time to solve that, and so I think we're going to have to turn to solar radiation management in a variety of different forms. I do have, and one of the forms is obviously iron salt aerosol, which can scatter light back and can help by reducing methane. But I have a couple questions about that. If I'm not mistaken, I was under the impression that methane has a half-life of about 12 years, so it would take natural hydroxyl radical oxidation about 60 years to remove excess once it stops growing. Is that correct?
I think so.
Yeah. Okay. So if my question is, why not focus aggressively and primarily on emissions reduction, such as CO2 and CH4 release, including the suppression of pipeline leakage, wellhead leakage, and fugitive methane losses for that, and for major CO2 reduction, and then just focus secondarily or in parallel on other albedo enhancements. Okay, the marine cloud brightening, various. There's about a dozen different ways of doing that, and then just wait for natural hydroxyl radical oxidation to remove the excess in about 60 years' time.
Well, from a CO2 point of view, emission reduction, we've emitted 2 trillion tons of CO2 into the atmosphere.
Right.
Up to date in all of our yesterdays, and it has a half-life of a couple of centuries.
That's correct.
In the atmosphere, right? So even if we were tomorrow, by some miraculous process, eliminate the 38 billion tons of additional CO2 that's going to go into the atmosphere in the next year, it has an almost inconsequential effect on the 2 trillion ton overdose that's already in.
I would agree. I would agree, and that's my point. There isn't time to solve the problem by any CO2 means. Okay, and that's why we need to.
Albedo can do it, right?
That's my point. That's not CO2. Yeah, so I'm saying that solar radiation management via about a dozen different albedo enhancement methods is the only thing that could move fast enough to do it by the 2040s or 2050s.
Okay, so John Martin's 50,000 tons of iron, John Martin's rock dust, at a cost of $50 a ton, right, is sufficient to produce enough to feed the plankton, the phytoplankton, ocean photosynthesis, to produce enough albedo to engage in the most dynamic, planetary cooling mechanism that we can imagine. Right.
I think Bob, we'll move on now. We've got Ron Bateman next.
Yeah.
Thank you, Robert. I just wanted to respond to Bob Fry's comment and Russ's that exchange, the most recent exchange. We and also add on to Dennis's announcement about the conference. We are actually proposing a number of methods, including methane emissions reduction, black carbon emissions reduction, bunker fuel, relaxation of the IMO regulations in the high seas, in addition to, of course, SAI and possibly MCB as methods to achieve short-term, near-term cooling, that is within the next 50 years, to possibly achieve that on a global scale. So I think I just would like to acknowledge that this is in our efforts to, this is the HPAC near-term urgent response, near-term cooling working group. We have been really trying to isolate all the different ways in which we can possibly achieve cooling, not just reducing the rate at which warming is increasing as emissions reduction does, or drawdown will take a very long time to get enough drawdown to actually get significant cooling. So I would agree with those. I think that those other methods are important to consider, and they do, of course, merge with the emissions reduction agenda. It's just you're focusing on short-lived. There are some references call them as short-lived short-lived climate pollution, SCPL. Kinds of greenhouse gases and particles, as it like black carbon. So I just wanted to add that comment. That is part of the I think the what we will be proposing in that conference.
Thanks, Ron.
Yeah.
Russ, do you have any comment?
No, I look at it, like I said, we have to throw every spitball we can think of at the wall and see what sticks and works, right?
I wanted to take you to a question which was asked in the chat by John Hepworth. And if John is still here and would like to raise his question about moral hazard, he can do so himself. You around, John?
Yeah, I'm here. I guess, I tapped out of academic ecology in 1989 when a lot of this stuff was first, or I remember this being discussed fairly widely back then. And so my question is exactly as I put in the chat, like, even if it works, aren't we granting the fossil fuel industries a pass? Isn't the difficult work the social engineering that's necessary? And I keep doing this napkin math, and I might be completely out to lunch on this. But if we talk about 2 trillion tons of excess carbon, and we divide that by 8 billion people, that's 250 tons of excess carbon per person. And in some of the carbon markets, they're pricing carbon removal at 200 per ton, which is like 50K a person, which to me, and again, you guys are the experts. I mean, it doesn't seem like a big number. So to me, it's the social engineering that's lacking. Anyhow,
I might just repeat your question as it is in the chat, John. You asked, isn't there a risk that even if it worked, it would perversely slow down the transition away from fossil fuels by reducing the urgency? So, Russ, what's your thoughts on that?
Oh, well, that has been the attack vector on this topic since the beginning, right? John Martin encountered that as he was attacked in the very first days of this by people who said, you're going to write a papal indulgence and give it to the fossil fuel industry, murderers of nature, right? And we can't let the bastards off the hook like that by providing a solution that takes them off the hook as the source of emissions. But the crisis is so severe, right, that no amount of, ocean acidification, so CO2 plus, H2O plus CO2 goes to H2CO3 in the ocean, which is acid. And the ocean has become less alkaline in the past many decades, which is called ocean acidification. But the rate at which it's acidifying is so dramatic. I talk with colleagues who are really sincere, dedicated, fantastic scientists, and they think doomsday is the year 2040 for the pH, for the ocean pH to reach the point at which the vast majority of life in the ocean will not, as we know it, will not be possible by the year 2040. This is not a 2-degree warming of the climate. This is a 90% loss of life in the oceans by the year 2040, right? And the only solution for ocean acidification is to redirect that CO2 from its acid-forming reaction, which it does by default, right? H2O plus CO2 by default becomes acid in the ocean. The only possible solution to that is to employ the power of the sun and photosynthesis to redirect that CO2 into becoming more ocean-like, right? And so as urgent as a holding the global warming to 2 degrees might be, I think holding the loss of ocean life to only 2% loss instead of 90+% loss faster, more deadly, right? More certain is a far more important goal. So the problem of of climate change is it takes all the bandwidth, right? Everybody talks about the climate change stories that we're familiar with talking about, and we're ignoring this dire situation that's been occurring in the ocean, and ignoring this miraculous uh, uh, power of the dust, right? And the
So, Russ, I
amount,
think what you're getting at is there's an order of magnitude problem that if we cut emissions, we might remove millions or maybe even tens of millions of additional CO2 that would have been added anyway, but it's not on the scale that's required in order to stabilize the climate. And like that's where the ocean iron is just absolutely critical to the planet itself, because if we don't restore ocean, and so the idea that it's a diversion from cutting emissions, which is more important. It's just not true to say that cutting emissions is more important than restoring the ocean balance.
Yeah. I mean, like it won't matter if it gets 2 degrees warmer at the beach. I mean, like I read last, in the summertime, the ocean water at Miami Beach is reaching the temperature of a hot tub. Right. So now lifeguards in the summertime at Miami Beach are now patrolling the beach, telling parents of young children that they must not allow their children to go into the ocean because the temperature of the ocean is so high as to be a health hazard for young children. Right. So, I mean, that is the effect of global warming. Right. But if the ocean acidification scientists are correct, and that following 2040, the water won't be too warm to be dangerous, it will be too toxic. The ocean water at Miami Beach will be so toxic as to be dangerous to the health of the children. Well, nobody will go to the beach. Nobody's going to go to the beach of a dead, fetid, stinking sea, right? So there's some protection. So it really is this problem of like, how do we change the point of view to include the plight of the ocean in our discussions instead of it always being about climate issues, right? Which
we've just got 3 minutes to go, so I'll go back to Greg Slater for a final question.
Thank you. I'd just like to know if you have everyone is trying to scale up various techniques to cool albedo, et cetera. What would be your ideal plan for scaling up ocean pasteurization in as realistic way as you could? And are you getting money? Are you getting interest from sources that this can be done? What's the scale up time that you could do, the fastest you could do? That's the question.
Well, following the 50 years of really sound science of the research side of the R&D process that's already taken place, the deployment schedule can be remarkably fast. So I think that and the cost of capturing and sequestering blue carbon, which is specified in the Paris Agreement as a tradable carbon credit. The cost of producing that's not $200 a ton, it's $2 a ton, or maybe 20 cents a ton, right? So the cost of doing it is remarkably small, right? And it's immediately deployable because it's the technology of measuring carbon in the ocean and plant growth in the ocean is very high tech. But the technology of replenishing the dust is the technology of mixing muddy water on the deck of a boat and sprinkling it into the prop wash as you drive back and forth across the pasture. It's as low a tech and as dirt cheap a solution as anything on this planet has ever been, right? And it can be immediately deployed at a global scale in time to save the planet. Well, to cool and save the planet, because the first thing we're going to see is a dramatic cooling effect because of the albedo, right? And the second thing we're going to see immediately is the production of fish, right? Is the increase in the weight of fish that are there and the number of fish that are growing. And then we're going to see the seabirds come back and the whales are going to be more numerous and healthy. And then over the course of a few years that it's going to take to get through the verification, certification, and monetization of the blue carbon credits, will eventually get the blue carbon credits into the climate marketplace, where that market still exists, which doesn't look like it'll be the USA for the next 4 years.
Well, Russ, I'd like to thank you for joining us for this conversation with HPAC, Healthy Planet Action Coalition. It's been very good to see you in person and hear your perspectives on these issues. I think there is just so much to discuss around this this whole topic. I find the politics just absolutely fascinating. And Peter Gross has made a comment about blue carbon credits. They're not ocean related, but maybe you're talking about a different type of blue carbon credits. That's, but we won't go into that now. We're out of time. So congratulations, Russ, on being a pioneer in this work and just opening up the public awareness and debate around the role of iron in the ocean. And pasture replenishment, I think, is a really interesting way of framing it. Just increasing restoring the lost biomass of the world ocean is just a really critical planetary health problem, and I think it's a crisis that we're not recognizing it, and I think you're leading the way. So I'll just give you a final comment, Ross.
Well, replenishing the ocean and restoring the ocean pastures brings back the fish. That's one thing we know for certain, which makes this in competition with all the other technologies. This is the most delicious solution to climate change and ocean change on the planet, right? Because we're going to have millions of tons of additional fish to consume. Right. So.
Well, thank you everybody very much for joining this call. We've recorded it and it'll be up on the HPAC website reasonably soon, and I look forward to seeing you again, continuing the conversation. Bye-bye.
Okay, thanks. Bye-bye.
Thanks, Russ. Thank you.